China just pulled off what most aerospace engineers thought was impossible. On February 11, 2026, they landed a reusable rocket booster on their very first attempt. No explosions, no failures, no learning curve. The Long March 10 first stage executed a controlled, vertical splashdown in the ocean with pinpoint precision, while simultaneously conducting the most dangerous spacecraft abort test ever attempted. They generated nearly 1,000 tons of thrust, enough force to lift 10 fully loaded Boeing 747s at once. You heard that right, and what happened in those 8 minutes of flight just changed the entire global space race. The Twin Miracles, February 11, 2026. Wenchang Space Launch Site, Hainan Province. Two impossible things happened at once. The Long March Chapter 10 rocket prototype ignited 7 liquid oxygen kerosene engines in parallel, creating a column of fire that shook the launch complex. But this was not a normal launch. This was the most technically complex test flight in Chinese space history. Maybe in any space program's history. Strapped to the top of that rocket was the Mengzhou spacecraft, China's next-generation crew capsule designed to carry astronauts to the moon, and they were about to deliberately trigger an emergency. The test had 3 simultaneous objectives that would each be career-defining achievements on their own. Verify the spacecraft's maximum dynamic pressure abort capability. Demonstrate the rocket's multi-stage parallel operations. Test critical return and recovery technologies for the booster, all at the same time. All on the first try. Here's why that's insane. Maximum dynamic pressure, called max Q, is the moment during ascent when aerodynamic forces on the spacecraft reach their peak. It's the most violent part of any launch. Air pressure, velocity, and structural loads all hit their maximum at the same instant. If something goes wrong at max Q, you have milliseconds to escape before catastrophic failure. SpaceX learned this the hard way. Blue Origin learned it the hard way. Russia learned it over decades. You test abort systems gradually, pad aborts first, then low-altitude aborts, then subsonic aborts, then finally max Q, after you have eliminated every possible variable. China just skipped straight to the hardest test. The rocket climbed through the lower atmosphere, accelerating faster with every second. Velocity built, air pressure increased. The 7 engines thundered at full thrust, pushing the Mengzhou capsule toward the moment of maximum aerodynamic stress. Then, it happened. The abort sequence triggered right at max Q. 8 powerful solid rocket motors built into the spacecraft's launch escape tower ignited simultaneously. 34,000 pounds of thrust erupted in an instant, yanking the capsule away from the rocket at forces that would crush an unprepared human body. The Mengzhou separated cleanly. Grid fins deployed to stabilize the capsule during its violent flight through the atmosphere. The spacecraft rotated, adjusted its orientation, and prepared for splashdown. Parachutes deployed in sequence, drogue chutes first to slow the descent, then main chutes blooming like white flowers against the blue sky. The capsule hit the ocean under full parachute control. Recovery teams were already moving in. But that was only half the story. While Mengzhou executed its escape, the Long March 10 booster kept flying. This is where things get really interesting. The rocket had just lost its payload in a deliberately triggered abort. Most boosters would tumble out of control after that kind of event. Not this one. The first stage continued its powered ascent to the predetermined altitude and speed. The engines shut down exactly on schedule. Now came the hard part. Turning a 15-story rocket around in mid-flight and bringing it back to a specific point in the ocean. This was a Herculean maneuver. The booster began its unpowered coast upward, still climbing on momentum. At an altitude of about 68 miles, technically in space, the rocket started flipping itself end over end. Reaction control thrusters fired in precise sequences, rotating the massive vehicle from nose forward to tail forward. Control was everything. 4 grid fins deployed like mechanical wings. These are not decorative. They are critical aerodynamic control surfaces that give the booster maneuverability during re-entry. Each fin can deflect independently, allowing the flight computer to steer through the upper atmosphere. This is critical engineering. At about 60 miles up, the real test began. 2 of the 7 engines reignited for the boost back burn. Think about what is happening here. The rocket is falling backward through space. The engines fire forward, slowing the descent and pushing the booster back toward the recovery zone. The guidance computer is calculating trajectories in real time, compensating for wind, atmospheric density, and 100 other variables. The engines shut down again. The booster entered aerodynamic deceleration, using atmospheric drag and those grid fins to bleed off velocity. This is the phase where SpaceX lost multiple Falcon 9 boosters due to too much heat, too much stress, and control systems failing under extreme conditions. Deceleration was the test. The Long March 10 handled it perfectly. At about 400 feet above the ocean surface, 3 engines ignited for the final landing burn. The rocket hung in the air, balancing on a pillar of fire. The onboard tether mechanism deployed, simulating the capture system that will be used for ground-based recoveries. This was the precision phase. At 16 feet altitude, the booster achieved a quasi-hovering state. The engines throttled down to the bare minimum needed to prevent acceleration. Then, with absolute precision, the rocket executed a controlled splashdown into the predetermined sea area. Vertical, intact, mission accomplished. Recovery vessels swarmed the landing zone. Cameras captured the booster floating in the water, grid fins still deployed, looking exactly like it was designed to be reused. Recovery teams moved quickly. The telemetry data told the full story. Every single system performed within nominal parameters. The abort sequence worked flawlessly. The booster recovery worked flawlessly. China had just demonstrated 2 breakthrough capabilities that took other space programs years to develop on the first try. But this wasn't luck or some one-time achievement. The technology nobody saw coming. The Long March 10 is a beast of engineering that hides its sophistication behind elegant simplicity. Start with the basics. The rocket stands approximately 180 feet tall in its prototype configuration. The full operational version will be even larger. It uses liquid oxygen and kerosene propellant, a proven combination that offers excellent performance and storability. 7 engines arranged in a circular pattern provide thrust. Each engine generates over 140,000 pounds of force. Together, they produce nearly 1 million pounds of thrust, making this the most powerful single-core Chinese rocket ever tested. But raw power is only part of the story. These engines feature deep throttle capability. They can reduce thrust to 30% of maximum while maintaining stable combustion. That is essential for landing. You cannot just turn rocket engines on and off like a light switch. The combustion process has to remain stable across a huge range of thrust levels, which requires sophisticated engine design and control systems. The engines can also restart in flight. This sounds simple until you understand what is actually happening. After the initial ascent burn, the engines shut down. The combustion chambers cool slightly but are still glowing hot. Residual propellant is boiling off. The turbo pumps have spun down. Then the flight computer says ignite, and everything has to work perfectly. The turbo pumps spin back up to operational speed, tens of thousands of revolutions per minute. Propellant flows into combustion chambers with uneven temperatures and pressures. The ignition sequence triggers in an environment completely different from ground ignition. One mistake and you get a hard start. An engine explosion that destroys the vehicle. The Long March 10 engines restarted twice during the test, flawlessly, both times. The guidance, navigation, and control systems are where China really flexed. The booster uses a combination of inertial measurement units, GPS receivers, radar altimeters, and ground-based tracking to know exactly where it is at every moment. That data feeds into a flight computer that makes hundreds of adjustments per second. During the boost-back burn, the engines gimbal constantly, tilting the thrust vector to steer the rocket. The grid fins deflect to provide additional control. All of this happens autonomously because radio signals are not fast enough at those speeds and altitudes. The rocket has to make every decision itself. The structural design incorporates advanced materials throughout. It uses aluminum-lithium alloys for the propellant tanks, lighter than standard aluminum, while maintaining strength at cryogenic temperatures. It also uses carbon fiber composites in the interstage sections, reducing weight without sacrificing structural integrity. Lighter materials throughout increase performance. The grid fins themselves are engineering marvels. They deploy at supersonic speeds in thin atmosphere. They have to withstand extreme heating during re-entry. They need to remain functional after being subjected to launch vibration, thermal cycling, and aerodynamic loads. They have to deploy reliably every single time, because one failed fin means loss of control. China's solution uses titanium construction with a honeycomb internal structure. Maximum strength, minimum weight, excellent thermal properties. Then there is the onboard tether mechanism, a system nobody outside China had seen before this test. Instead of landing legs that add weight and complexity to the rocket, the Long March Chap-10 will use a ground-based net recovery system. 4 tether attachment points on the booster connect to a massive net structure on the ground. Net recovery shifts mass and complexity off the booster and onto the ground system. The rocket descends to hovering height, the tethers engage, and the ground system handles the final capture and stabilization. This transfers weight from the rocket to the ground infrastructure, increasing payload capacity. It is brilliant, innovative, and completely different from SpaceX's approach. But here is what makes all this truly shocking. This technology did not appear overnight. You do not develop engine restart capability, precision guidance systems, advanced materials, and novel recovery mechanisms in a few months. This represents years of quiet development. Static fire tests in August and September 2025 validated the engines and systems, but those were just the visible tip of the iceberg. How many years of research preceded those tests? How many subscale prototypes were built and tested? How many simulations were run? The West is now scrambling to answer those questions. Intelligence analysts are reviewing satellite imagery of Chinese test facilities. Aerospace engineers are studying every frame of video from the February 11th test. Everyone wants to know how China compressed what should have been a decade of development into a program that emerged fully formed. The answer is becoming clear. They did not rush. They just worked in private until they were ready to demonstrate a mature, operational capability. And that capability is about to change everything. The moon race just got real. NASA has been planning its return to the moon for years. That includes the Artemis program, the Space Launch System, and the Orion capsule. Billions of dollars have been invested. Political capital has been spent. International partnerships have been formed. The plan is straightforward. Artemis 2 will send 4 astronauts around the moon, currently scheduled for launch in March 2026. Artemis 3 will land humans on the lunar surface in 2028, using a modified SpaceX Starship as the lander. That timeline just became a lot more uncertain because China is not planning. China is executing. The Long March Chap-10 is specifically designed for lunar missions. The operational version, with 3 stages and 2 bundled boosters, will have enough carrying capacity to send the Mengzhou spacecraft and the Lanyu lunar lander toward the moon. Together, these systems form China's complete crewed lunar architecture. And they are all testing ahead of schedule. The Mengzhou capsule just proved it can protect astronauts during the most dangerous abort scenario. The spacecraft's heat shield, parachute systems, and recovery mechanisms all worked perfectly. That is one less thing China needs to validate before putting humans inside. The Lanyu lander has also passed its tests. In late 2025, China successfully demonstrated the lander's ability to touch down and take off from a simulated lunar surface. The vehicle's legs, descent engines, and ascent engines all performed as designed. Put it together, and you have a complete lunar mission architecture that is already proven in testing. The only thing left is the actual moon flight. China's stated goal is to land taikonauts on the lunar surface by 2030. After the February 11th test, that timeline looks increasingly realistic. Some analysts now think China could beat that target, possibly landing as early as 2029. Here is why that matters. The last humans on the moon were Eugene Cernan and Harrison Schmitt. during Apollo 17 in December 1972. For over 50 years, no human has walked on another world. The United States has held that achievement as a unique point of pride and technological supremacy. If Chinese taikonauts plant their flag on the moon before American astronauts return, the psychological and geopolitical impact will be enormous. It is not just about bragging rights. It is about demonstrating technological capability, inspiring the next generation of scientists and engineers, and establishing precedents for lunar exploration and eventual resource utilization. The moon has strategic value beyond symbolism. The lunar South Pole may harbor water ice in permanently shadowed craters. Water means propellant. Propellant means the ability to refuel spacecraft for missions deeper into the solar system. Whoever establishes infrastructure at the lunar poles gains a massive advantage in CIES lunar space. China's lunar program includes plans for the International Lunar Research Station, a permanent base on the moon developed in partnership with Russia and potentially other nations. If China lands first, they will have years to establish their presence, test technologies, and build infrastructure before NASA's sustained lunar presence begins. For SpaceX, the pressure is even more intense. The company's entire Artemis 3 participation depends on Starship being ready to serve as a lunar lander. But Starship is still in testing. Recent flights have shown progress, but the vehicle has not yet demonstrated the full mission profile needed for lunar operations: orbital refueling, long-duration coast, precise lunar landing, and return to orbit. Meanwhile, China has just demonstrated that their lander works. Their crew capsule works. Their heavy-lift rocket works. They are not talking about what they will do someday. They are showing what they can do right now. Elon Musk has publicly stated that SpaceX needs to accelerate Starship development. The company is already working on Starship version 3, a larger, more powerful iteration with improved capabilities. But even with SpaceX's rapid development pace, catching up to a program that is already flight testing is challenging. The competitive dynamics have fundamentally shifted. For decades, the assumption was that America would return to the moon first because no other nation had the technology or resources to compete. That assumption is now dead. China has the technology, they have the resources, and they have the political will to make it happen. The race to the moon is no longer hypothetical. It is happening right now. But the implications extend far beyond one landing site. The economic revolution nobody's talking about. Reusable rockets aren't just cool technology. They're the key to making space affordable. Think about the economics. A traditional expendable rocket might cost $150 million to build and launch once. Every mission requires a brand new vehicle. The entire rocket, engines, structure, avionics, everything burns up in the atmosphere or crashes into the ocean after a single use. It's like building a 747 for every single flight and then destroying it upon landing. SpaceX changed that equation with Falcon 9 reusability. Reuse the first stage 10 times and your per launch cost drops dramatically. Maybe $70 million per flight. Reuse it 15 times and you're down to $50 million. The rocket becomes an asset instead of a consumable. China just bought into that same economic model. But here's what makes this different. SpaceX had to figure everything out through trial and error. They spent years and hundreds of millions of dollars learning how to land boosters. Each failure was expensive. Each iteration required building new hardware. China watched all that happen. They studied the problems. They developed solutions in private, and now they're implementing a mature reusability program without going through the expensive learning curve. That means lower development costs, faster time to operational capability, and potentially more aggressive pricing in the commercial launch market. Chinese launch providers have already been competing on price. The Long March rocket family offers launches at rates that undercut some Western providers. With reusability, those prices can drop even further, while remaining profitable. Imagine a scenario where China offers heavy lift launches for 60% of NASA's current costs. International satellite operators start making phone calls. European companies reconsider their launch providers. The global launch market gets very competitive very quickly. But the bigger economic impact is what reusability enables. Satellite megaconstellations become viable. China has announced plans for multiple constellations, Guowang with 13,000 satellites, Hongyan, and G60. These networks would provide global internet coverage, compete directly with Starlink, and extend Chinese telecommunications infrastructure worldwide. Without reusability, deploying 13,000 satellites is prohibitively expensive, with reusable rockets launching 60 satellites at a time on a weekly cadence. Suddenly, it's achievable within a few years. Space station expansion becomes affordable. The Tiangong space station currently has 3 modules. The design allows for unlimited expansion, additional habitation modules, scientific laboratories, power generation, larger solar arrays. With reusable launches, China could scale Tiangong to rival or exceed the International Space Station within a decade. Lunar infrastructure stops being a fantasy and becomes an engineering project. Sending 10 tons of equipment to the moon might cost $500 million with expendable rockets. With reusability, maybe $200 million. That's the difference between 1 mission per year and 5 missions per year. The economic mathematics completely changes when launch costs drop by 60 to 70%. Chinese companies are already developing commercial space stations, space-based manufacturing, and orbital tourism ventures. Reusable rockets make all of these businesses more viable. Lower launch costs mean lower barriers to entry. More companies can afford to try. More experiments can be run. More innovation happens. There's also a manufacturing angle nobody's discussing. Reusable rockets need to be built for multiple flights from the start. That means better materials, more robust design, stricter quality control. China's aerospace industry is being forced to level up its manufacturing capabilities to meet these requirements. The same technologies that enable rocket reusability have applications in other industries. Advanced materials, precision manufacturing, automated control systems. These innovations ripple outward into the broader economy. Lower launch costs mean China can put more satellites in orbit for the same budget. More communication satellites, more navigation satellites, more Earth observation satellites. More of everything. Space-based capabilities directly translate to terrestrial advantages. Better weather forecasting, precision agriculture monitoring, disaster response coordination, navigation systems that do not depend on American GPS. Reusability does not just make space cheaper, it makes space power more accessible. And China is about to have a lot of it. What happens next? The February 11th test opened a door that can't be closed. Within weeks, China's space agency announced the next phase of Long March 10 development. The full 3-stage configuration with bundled boosters is being prepared for orbital test flights. The timeline suggests the first full-scale launch could happen in late 2026 or early 2027. That's the rocket that will send humans to the moon. Meanwhile, the Mengzhou spacecraft is being prepared for additional tests. The next abort test will verify high-altitude scenarios. Then comes an uncrewed orbital flight to validate all systems in the space environment. Only after that will China put taikonauts inside for a crewed mission. The Lanyue lunar lander is following a parallel development track. Ground tests are ongoing. A low Earth orbit demonstration mission may happen in 2027 to validate descent and ascent capabilities in space. All of these programs are converging toward the same goal: a crewed lunar landing around 2030 or earlier. But China isn't stopping there. Plans for a permanent lunar research station are advancing. The station would be located at the lunar South Pole, where permanently shadowed craters may contain water ice. Chinese scientists have already selected potential landing sites based on Chang'e lunar mission data. The first elements could land by 2032. Habitat modules, power systems, scientific instruments, rovers for exploring the surrounding terrain, all delivered by reusable Long March 10 launches that make the economics work. Russia has expressed interest in participating. Other nations are watching carefully. If China establishes a successful lunar base, it becomes a magnet for international collaboration. Just like the International Space Station, but without American veto power, the satellite constellations are also moving forward. Test satellites for the Guowang system have already launched. The full deployment will begin once reusable rockets are operational. 13,000 satellites providing global internet coverage, positioning services, and communications infrastructure. That's not science fiction, that's an engineering project with a budget and a timeline. SpaceX is responding by accelerating Starship development. The company needs to demonstrate Starship's full capabilities to maintain its competitive position. That means successful orbital refueling, lunar landing demonstrations, and proving the vehicle can operate reliably on the timeline NASA needs. Blue Origin is also pushing forward with its new Glenn rocket and lunar lander programs. Jeff Bezos has made lunar infrastructure a priority for the company. The result is a genuine space race, not government versus government like Apollo, but a complex competition involving multiple nations and private companies, all pushing toward the same destination. And it's being driven by economics as much as prestige. The nation or company that establishes infrastructure on the moon first gains massive advantages in cislunar space. They set precedents for resource utilization. They demonstrate technologies that others have to match. They attract talent and investment. The Long March 10's February 11th test proved China is a serious competitor in this race. Not a distant follower trying to catch up, but a leader demonstrating capabilities that match or exceed what anyone else has shown. For the United States, this is a wake-up call. NASA's Artemis program has been delayed multiple times. The Space Launch System is expensive and limited in flight rate. Commercial partnerships with SpaceX and Blue Origin are critical, but still developing. Meanwhile, China is methodically checking boxes. Crew capsule tested, lander tested, reusable rocket tested. Each milestone brings them closer to putting boots on the lunar surface. The next few years will determine who gets there first, and that question matters far more than simple bragging rights. Because the real prize isn't one landing, it's permanent presence, it's infrastructure, it's the ability to operate in cislunar space as easily as we operate in Earth orbit. Reusable rockets are the technology that makes that future possible. They slash costs, they increase flight rates, they transform space from an exotic destination into an accessible frontier. China just demonstrated they've mastered that technology on their first operational test. The Long March 10 booster that splashed down in the ocean on February 11th will be recovered, refurbished, and potentially flown again. That single vehicle might launch a dozen missions over its operational lifetime. Each flight will be cheaper than the last, as the refurbishment process is optimized. Multiply that across a fleet of reusable boosters, and you've got the foundation for a true space economy. The race to the moon is really a race to make space affordable. China just proved they're running faster than anyone expected, and they're not slowing down.